Yes. The which? Lie derivative? Yeah.
We find it on derivatives, and then we said that it was a derivation, so we could define it
Tensors.
on tensor fields.
So on. Go back to it, yes.
But how can we find that is the derivation just by defining it on tensor fields?
Well, the intuitive meaning of the Lie derivative, as I think I said and was going to remind everyone just now, is an infinitesimal diffeomorphism. So anything that can, on which a diffeomorphism can act, can have a Lie derivative. So the most direct definition of the Lie derivative of a tensor field is to actually use that, perform the diffeomorphism on the tensor field, take the rate of change as a tensor field under the diffeomorphism about the identity. That's probably the most direct, but it is in fact a derivation. So you could use the opposite. You could use the other alternative definition that you said, and that would be also valid. Basically, because diffeomorphisms commute with all the operations of the tensor algebra, the tensor product, the contraction, addition of tensors, and so on. So because it does that, an infinitesimal diffeomorphism will automatically be a derivation. So the two definitions, either definition is adequate. Any other questions? Yeah.
Would you be able just to summarize all the different derivatives and when each one is?
Well, we have basically only really two derivatives. So the most fundamental derivative, they sort of intersect in the most fundamental case. The most fundamental case, given a scalar field, you can form its gradient, right? Then, given any tensor field, that's special to a scalar field. So if you ask for the derivatives that act on any kind of tensor, an arbitrary tensor field, there's only two that we've defined. One is the covariant derivative, which can act on an arbitrary tensor, and the Lie derivative, which can also act on an arbitrary tensor. Right? So those are the only two that we've defined. And so when I say they intersect, what I really mean is that we define the covariant derivative of a scalar field this way, and we define the Lie derivative of a scalar field through the gradient, if you like, that for a scalar field, it's just a directional derivative along the direction of the vector field C of the scalar field. So in this sense, for the scalar field, you don't need extra, both of the derivatives amount to the same thing, one being just a gradient, the other one being a directional derivative. In other words, a contraction of the gradient along a certain direction. But for general tensors, they're different, but they are related. And I showed you a formula how to express the Lie derivative in terms of so the Lie derivative of any tensor field. You can't go back, right? Because the Lie derivative doesn't itself know about the metric or any connection, and the covariant derivative, of course, depends on that, because it depends on knowing what is a local inertial, momentarily inertial frame of reference, and that only makes sense when you have a metric. So you can't hope to define the Lie derivative in terms. You can't hope to define the covariant derivative in terms of the Lie derivative, which exists on any manifold. It doesn't even require a metric, but you could hope to go the other way, and in fact you can, and we gave a formula for that, if you remember, which was equal to the sort of covariant directional derivative, the analog. I'll leave the indices off of T. The analog of this thing for the scalar, the general, plus correction terms, right? And then the correction terms all take the form of the gradient of the vector field. That's the argument of the Lie derivative acting on the tensor, so there's a sum of terms of that general form, where index go in here in the appropriate way, and contractions. So for each index of the tensor T, which is basically for each factor, each vector or covector factor that goes into the formation of the tensor T, is because of the Leibniz rule, you have another correction term coming from that represents either the Lie derivative. If it's a vector factor, it represents the Lie derivative with respect to C on that vector, or if it's a covector factor, it represents the Lie derivative with respect to C on that covector field. Okay, and we wrote down explicit. I won't write these down again. They should be in your notes. They look exactly like, in formation, they look exactly like the rules for taking the covariant derivative. I mean, they look like the rules that you would write down if you were just writing down the covariant derivative in a coordinate system and put here the Christoffel symbols, except there's a sign change. Okay, is that? So really, we only define two derivatives. The Lie derivative, which is an infinitesimal diffeomorphism, and is available in any manifold once you give the vector fields, of course, and the covariant derivative. Okay.
Yeah.
Okay. So what I want to do. Today is use the Lie derivative. I mean, the Lie derivative, as I mentioned last time, is a kind of symmetry or potential symmetry. I mean, it's an infinitesimal diffeomorphism. If the metric is invariant under that, then that represents a symmetry. And when there is a symmetry, you're used to the fact that there should be corresponding conservation laws. So mainly what I want to do is show how that works out, starting direct from the action. It's remarkable how much you can derive just working from the action principle. So we'll go through that, and then since this is such an important result, or an important feature of the theory, I thought I'll go through and then show by direct calculation how you derive the same results. The basic result that will be that given if this C is a killing vector, well, since this is just reminding everything, we say that C, if leak C of GAB equals 0, this is called a killing vector field, this vector field C. And the condition for it, just by applying these rules for forming the Lie derivative, is grad A CV plus grad B CA equals 0, if you express the condition in terms of the covariant derivative. So these are equivalent statements. And that's called a killing vector. When you have a killing vector, which represents an infinitesimal isometry, in other words, an infinitesimal diffeomorphism that preserves distances and angles, in other words, it preserves the metric, when you have that, then we'll see that along a curve, gamma, which is a geodesic, either a null geodesic, that's important, like light-like one, or time-like, then, because we'll use both, then this is conserved. It's just the component of the momentum along the geodesic is conserved, along the component of the momentum along the killing vector is conserved along the motion of the particle. It takes the same value everywhere on the trajectory. But so more generally, what we're doing now might be called what you can learn about the metric. I mean, we're going to be studying particle motion in a fixed metric, so like especially the Schwarzschild metric, but for the moment, let's keep it general. So we'll basically be studying geodesic motion of particles. But the aim here is, from a certain point of view, the aim is what the underlying question is, what can we learn about the metric by exploring it with different kinds of test particles? Just like the planetary orbits help us to explore the metric around the sun. So there's a word for that, where you think of the metric as fixed, and you don't take into account the gravitational field of the particles, which would influence the metric, the so-called back reaction. So these are called test particles, particles whose back reaction are ignored, and especially the case of Schwarzschild will be the main one of interest. And so, but these test particles will also include light, or what we might call light, if we ignore the question of polarization. So basically, we just working out the trajectory, the world line of what you might call a test photon. Okay. So some reading for this is section 7.4 and 11.1, and in Wald pages 149 to 52, and section 6.3. Okay. So the first thing, as I said, it's amazing how much you can derive from an action principle or a variational principle when you have one. So in this case, we do have one. So let me write, but we want to also include light, like world lines. And the action principle we wrote down before, if you remember, was the integral of d tau. This is probably familiar to you also from special relativity, where d tau, that means just that d tau is the square root. I'll just write it as x dot squared. So that's okay, and that works for positive mass, and it has a nice geometrical character. It depends only on the world line gamma and on nothing else other than the metric, of course. No auxiliary quantities, however. But a field theorist probably would never, if they didn't already know this, they probably never would have written down this Lagrangian because it has a square root. And it's kind of a article of faith that you only write down polynomials. So you might take the point of view, well, so much for field theorists. By field theorists, I mean quantum field theory, or more specifically, what probably effective field theory. So you might say, well, so much for effective field theory. But on the other hand, it is convenient to work with polynomials. And what's more important is not convenience, but if we want to deal with null geodesics, where this is zero, right? So along the world line of a light-like geodesic, of course, this x dot squared, that really stands for g a b dx. Oh, I left. I should have put here d lambda. No, what am I saying? Oh, this is all right. I should have put d tau. No, I should have put d lambda. So I'm thinking of this dot as d by d lambda. So what's really going on is that this is the square root of minus dx squared. The lambdas drop out precisely because of the square root. The parameterization drops out. It's just an illusion that it's there. But what this really is dx a dx b, right? That's what that stands for. And when dx is a null vector, of course, this is 0. But the square root of 0, 0 has a singularity. 0 is a singularity of the square root. So when you want to vary that, it's not going to work if you vary about 0, if you want to differentiate the square root about 0. So that's a more important reason why we can't, at least as far as I know, use this kind of action to describe photons. However, there is another action so that does work. So we can ask, can we find a polynomial action, a Lagrangian? And so let's see what might we think to write down. So the simplest. So now when I don't take a square root, this lambda is not going to drop out, and so it's actually going to survive. And later, maybe after we see how it all works, we'll come back and I'll raise the question, what is its physical meaning? And I'll suggest an answer, but I'm not even sure that that's the best answer for it. But let's suppose we do that. So we want to do some sort of integral with respect to the parameter lambda of something along the world line. So what is the simplest term that we can write down? So now I am reasoning the way an effective field theorist would reason as a motivation. So what's the simplest thing that we can write down? Well, the simplest thing I can put here is what I've already put here, which is 1 or nothing, basically. So this, if you were thinking in another slightly different context, you might call it, in other words, if the integral was over space-time and not just over a world line, you might call this a cosmological constant term. Anyway, it's the integral of just the 1. The next simplest thing that you can write down, I'm doing this also because when we come to the Einstein equations, this is exactly how it will be. The simplest thing you could write down will be a volume integral, and the next simplest will be the scalar curvature, and that gives you classical general relativity. So the next simplest thing we can put here after 1 is just the square of the gradient. Gradient here just means derivative along the world line gamma. And then the only other things after this I could write would involve higher powers of this or more powers, more derivatives, like I could bring in the acceleration and so on. But this would correspond to what you might call kinetic energy in the kinetic energy in the if you're dealing with a field, or it would also correspond in the gravity case, as we'll see, to the Ricci scalar. So it's a second order, that is, it involves 2 derivatives. Of course, the Ricci scalar is not, of course, polynomial entirely in the metric, but it is polynomial in the derivatives. So that's another case where effective field theory doesn't really work in some sense, in that prejudiced sense anyway. So these are the simplest things we can write down, and it turns out that just a simple combination of them gives an action that correctly describes both time-like and null geodesics. Of course, when I say these are the only things we can write down, I'm treating the particle, this test particle, not only as a test particle, but I'm treating it as a point particle also. Right? So I'm assuming that it's completely described just by its world line, no extra structure like a polarization vector carried around, or in the case of something like a planet, which we'll treat when we come to Schwarzschild, I'm ignoring the fact that the planet is a finite-sized thing, and it has all kinds of internal structure, and it spins and angular momentum. We're ignoring all that. So this is either a photon without its polarization, or it's a planet, something like a planet without its size. So within that context, within that setting, there's nothing more we can write than these higher order things. So it turns out that the following, which is just a linear combination, just a certain combination of those two, yields the equations of motion we want. So this is action for the world line. M, of course, is the mass of the particle. And that's it. If you want to see this written out more fully, then with the metric made explicit, then it's convenient to write it like this. So it's GAB of x dxa d lambda dxb d lambda minus m squared integrated d lambda, where of course we're thinking here in all these cases, as always, that x is gamma of lambda. So it's a world line parameterized by this parameter lambda. And here, just like we saw when we did cosmology, we vary lambda freely. This is crucial at endpoints. But we fix x. And then what the variational principle says, of course, is under those conditions, the variation of the action to first order is 0. Now this works. We'll see that it works. But it probably should have some sort of deeper basis, which I don't know exactly what it could be. But for example, you might, I suspect, I think I might have even have done this once, but I can't remember if I did. I suspect that you can get it by a geometrical optics approximation to the wave equation, or what's called the Eikonol approximation sometimes. You're smiling, do you? Oh, I thought you were familiar with it. No. We might get a geometrical optic. We could probably get it one way or another by working out the geometrical optics approximation to the scalar wave equation. Of course, I haven't written down the scalar wave equation. Maybe I should mention it. So if we're dealing only with a scalar field, since we have a covariant derivative, now we can form, remember, in flat space, the wave equation is just this equation, where this is just the gradient dotted into itself with the aim of the metric, aid of the metric. The same thing can be done in curved space, and it leads to the same equation if you just define this box or this D'Alembert operator to be this, where now, of course, I'm raising and lowering, as always, the indices with the metric. So that just means GAB grad A. Better to write it the other way. Let's say GAA, so we don't have to worry, grad A, grad A. So just the contraction of those two. Once you have that, then you can write down the scalar wave equation. And this is the equation that describes propagation of a massless field. Would be the photon if the photon didn't carry polarization. And I suspect by thinking carefully about the geometrical optics approximation, that is the very short wavelength approximation to this, where the wavelength is much shorter than the curvature, than the scale of curvature, the radius of curvature of the space-time, that you could somehow derive this. But I don't know how to do that. So we'll just take it for now as an input and see where it goes. Before doing that, so now I want to use this to define the momentum, this PA that we talked about here, and then prove this conservation law along the killing vector. But let me make a couple of remarks first about action principles. So in the development that we're going to follow now, you will see that everything comes almost directly and almost with no work out of the action principle. So action principles are great when you have one, but it would be wrong to give an impression that you could do all of relativity just from action principles. I'm probably trying to do as much of it as I know how, but you can't do everything, because an important application of the theory, for example, is to the structure of stars, say rotating stars, instabilities of rotating stars, gravitational radiation by them, and so on. And in those, quite often, the viscosity, or think of accretion disks, in all of those situations, it can happen that viscosity is important. And in some of them, it can also happen that heat conductivity is important. Certainly, in principle, those are all going on. Inside the sun, heat is being conducted. If it weren't the sun, we wouldn't see the sun shining. And the sun is rotating and has complicated fluid motions. And so it has some viscosity. Sometimes you can get away with an approximation in which you ignore those things, but you can't always, and they're certainly there. And when you have to describe dissipation, which are both of those being examples of dissipation, viscosity and conduction of heat, whenever you have dissipation, it's generally impossible to write down a useful variational principle. Or in general, as far as I know, it's just impossible to write down a variational principle. And the reason is because one way of understanding why it can't be done is that when you do have a variational principle, you get these conservation laws, and they would tell you that the total energy is conserved, but some of the energy, when you have viscosity, some of the energy is dissipating into heat. It doesn't show up anymore in the field variables. You just have to add another variable, which is the entropy density or something like that. But then it won't be conserved, or it won't be conserved in the way that comes from the variational derivative, which basically allows, what's the opposite of dissipation? It allows things to go in both directions in time. It doesn't have a fundamental direction of time built into it. And so since in the real world dissipation doesn't run backward, the equations that you write to describe them, the diffusion equation and so on, those equations can't be derived from a variational principle, as far as I know. So it's important to realize that for some purposes, it's the equations of motion, and when we come to gravity, that'll be the Einstein equations, that they're actually more basic, they're of more general applicability than the action from which we derive them. Now, of course, what we know of quantum mechanics strongly suggests that the fundamental theories, whatever that means, are described by action principles. They are reversible at a fundamental microscopic level. But even if you take that as true, which I think it is true, even if you take that as true, that's driving you to deal. If you wanted to describe a star, that's saying you have to redescribe the star in terms of atoms. But then you can't describe the atoms as classical. You know that's wrong, and so you have to describe them as quantum. So you'd have to do quantum mechanics, and if you want to do the back reaction of those on the gravitational field, which you do, then you're ultimately doing quantum gravity. So that's a lot. So for practical purposes, we really are stuck with dissipative equations. The other comment that I wanted to make is that this notion of point particle that we're using, these test point particles, that's not really a consistent concept in general relativity, right? Because a point particle would be one of no extension, but if you try and squeeze something down to zero size, once you cross its Schwarzschild radius, it's going to form a black hole. And a black hole is not a point particle, it's an extended object. So there really is no such thing as a point particle in relativity. So to fully justify what we're doing, you'd have to deal with extended objects, either black holes, or, which is not the realistic case, often, sometimes it is, but often it's not, or more realistically, you have to deal with things like planets and stars, which are extended objects and have internal structure, and then you'd have to show that to some approximation, you can ignore all that, and you describe them by this action principle. Or maybe we could work with something else that's quasi-point-like, which is a wave packet. So so all these things, whatever they are, a wave packet, which is, if you like, the quantum description of a photon, a black hole. All these things are really extended up. The things which in practice we're really talking about here are always in some way extended. Or maybe they're not. Maybe in quantum field theory, you have real point particles, whatever that means, maybe. But then then you have to bring in quantum field theory, and then, as I said, via the Einstein equations, you'll be forced to do quantum gravity. So I'm just saying all this to point out that in writing this down and making this approximation of a point test particle, we're sweeping a lot under the rug. Nevertheless, it works very well, and people have justified those approximations in cases like this, black hole, star, wave packet. Although, as I said, it would be nice to show how I would enjoy seeing how the wave packet how you could derive this action directly from a geometrical optics approximation. Okay, so enough caveats. Now, let's take this action here and just vary it. So suppose we vary d lambda, just like we were used to doing in cosmology and in some of the homeworks too. So if you vary d lambda, you immediately see that it just produces minus dx squared over d lambda squared minus m squared equals 0, right? That's the variational. We vary d lambda and we set the variation of the action to 0. We'll get this equation. This implies that d tau squared, the proper time along the world line, which is equal, of course, to minus, with our signature, minus ds squared, which is minus dx squared, what I'm calling dx squared, is therefore equal to m squared d lambda squared. Or if we take the square root, d tau is equal to m d lambda. So what it shows you, first of all, if that m is not 0, it tells you that lambda is no more than just a rescaled proper time. So it's in some sense not a new degree of freedom once you impose this equation of motion that comes from varying lambda. However, it also shows you, of course, that in the massless case, d tau is 0, which we already knew. And, well, in other words, what it's telling you is that maybe we didn't know it, so to speak. I mean, we knew it in some form, but we didn't know it if all we had to work with was this. But now we know it because it tells us that in the massless case, the proper time elapsed to 0. In other words, the massless particle must move at the speed of light. Okay. So that's the first conclusion. Now let's also, what I want to do is relate this. We do relate the two action principles when they're both there. So in the massless case, as I was saying before, this action principle doesn't seem to work. But in the massive case, it does, as we know. So let's see if we can relate this more general action principle to the one that we already have. So let's plug in that. In other words, we'll put lambda on shell, as people say. In other words, we'll assume that the equation of motion that comes from varying lambda is satisfied. Sometimes people say integrate out lambda, but that's a very confusing language for it, thinking of the path integral. But anyway, we'll assume that lambda satisfies its equation. We'll assume that the equation, lambda satisfies its equation of motion, or the equation of motion that comes from varying lambda is satisfied. So what do we get then? We have the 1/2 integral. Now we had dx squared. We just saw that's minus m squared d lambda squared, which is minus d tau squared. So now I will now strictly assume that m is positive, so I can write this. So it's d tau squared over d lambda minus m squared d lambda. But if I take one of the m's and put it with a d lambda, I get d tau. So this becomes minus m, and I keep the other m. It becomes minus m d tau. And what does this term become? Well, remember, if I take if I take one of the d taus away, then it becomes m d lambda, and that cancels out, that gives us an m. So basically it equals, this also equals minus m d tau. And there's a 1/2 here, so the whole thing becomes minus m integral d tau, which was the other action we had. So we see that this new s agrees with the old s if m is greater than 0, and I don't know how, I'll just write it like this, that the variational equation for lambda is satisfied. So that's nice. So we can see right at the level of the action itself that we'll get the same equations of motion in the massive case. Because now the only thing we have left to vary, once we vary d lambda, the only thing we have left to vary is the world line itself, and for that, the actions are the same. So we'll get the same solutions. One other comment, just of general interest, might be, so we see here that in the massive case anyway, we have two distinct action principles, one involving just purely geometrical, involving just the world line itself, but it has a square root in it. And the other one, without a square root, that's just a quadratic, just like a square of a gradient or of a derivative, but that involves this extra auxiliary object, lambda, living on the world line. So if you're familiar with string theory, or that is the action for a two-dimensional membrane in 4 dimensions or whatever space-time, you might recognize a similarity here, which is that in the case of string theory, there are also two such actions. The one that's analogous to this, it's purely geometrical. It basically just takes the area of the world sheet as the action. It's called the Nambu or Nambu-Goto action. And then the analogous one that introduces a new object on the world sheet, which in that case is symmetric, and integrates over it too. That's called the Polyakov action. So there's a sort of that's just a side comment, but maybe worth writing it down. That this integral d tau corresponds to the Nambu-Goto action, and this integral of this more complicated one, dx squared minus m squared d lambda, whatever it was, 1/2. This was, anyway, we don't need the exact factors. They correspond to what's called the Polyakov action in string theory. One last comment is that sometimes people will write this action with a little bit of, I think, what you might call unnecessary I don't know what to call it, overkill, or it's not killing anything here exactly, but it's one of these things where you're doing more than you really need. You're making it, in some sense, more complicated than you need to. Sometimes people would write it in terms of something that's like, but again, this is a useful analogy, a useful thing to look at, because it makes a nice simple analogy, just as this was a nice simple analogy to string theory. It's also a nice simple analogy to the what's called the ADM formulation, or the canonical way of writing down gravity, the general relativity, or the Einstein equations. And then in this case, what they would do is they would say, I don't like the fact that you said we have to vary lambda freely at the endpoints. I want to keep it fixed. So if you want to keep it fixed, then you're going to lose this equation of motion that told you that related proper time to lambda. So you say, okay, if you want to keep it fixed, that's okay. I'll just introduce another variable that I allow to depend on lambda, and I vary it freely. So in this, I'll get the same effect. And then the action will look like this. Now I have, so this is just another comment, really. It's not essential to anything we're doing. But if you write it like this, if you're familiar with the canonical way of doing general relativity, you recognize that this is like the lapse function. This plays the analog of the lapse. And what you've done by writing it this way is you've introduced a kind of superfluous variable, because you have lambda and you have n, and both of them are doing almost the same thing. The only slight difference is that this introducing n allowed you not to vary lambda at the endpoints. But otherwise, they're just redundant information. And this redundancy is what's called reparameterization invariance. So now I can use any, I can reparameterize lambda. That is, change it to any function of itself as long as I don't change it at the endpoints. And there'll be a corresponding change in n that will leave the action unchanged. And then it looks like I've introduced, and I have introduced, then a huge gauge invariance into this theory. But if you think, if you don't bother to do that, then that, in some sense, that gauge invariance isn't there. It's just something you chose to introduce. In fact, what you should probably do is think of, maybe I'll say this later again, but this d lambda, you could really think of this as a kind of free one form that you're defined on, that is a covector field, but a field only defined only on the submanifold, which is the world line itself. Okay. So now forget all that. Let's go back to the action and to that and to these conditions for getting the equations of motion. Once we have that conservation, we'll see that conservation of momentum, or of this particular component of momentum when we have a killing vector, follows with essentially no work at all. So I have to, if I define the momentum right, so if I define the momentum right, it follows with no work at all. Then you have to do a little work to see what is the explicit form of the momentum that you've defined, but it's not very much work either. So I'll define the momentum by this equation, which says we know that if we vary the world line and we fix the endpoints, then the variation of the action is zero. That is how we define the equations of motion. However, what if we don't fix the endpoints? So we don't fix the endpoint. In particular, suppose we have some curve here, this gamma. Let's fix the initial endpoint, but let's just, for simplicity, allow the final endpoint to vary, but not the initial endpoint. Then we'll get of course, we'll get a contribution from varying the final endpoint. Nothing guarantees that we won't. And I'll write it like this. So, meaning that these things PA and the variation of x should be evaluated at the final endpoint. And this funny halves equals, I'm using that to mean add a solution. In other words, before we took the variation, we had a solution. So this world line should be a solution of the equations of motion. Now we vary the final endpoint. You could also ask what happens if you vary lambda at the end, but we already, that's one of our equations of motion tells us that gives zero. So we don't have to worry. There's no point in worrying about it. So this is the definition of momentum. We call PA equal to the momentum. Now, if we can, now that it looks like it's just a definition, but of course, it won't be consistent if the variation in the action doesn't have the form of some quantity computed along the world line multiplied by just the variation, the final displacement. This is this delta x here. It could have a more complicated form. It could depend, for example, on the variation of the velocity at the endpoint and not just the position. Then I wouldn't be able to define the momentum this way. However, that doesn't happen precisely because when you go back and look at the action, you only see first derivatives, or look in this form, you only see first derivatives of x. Had I seen second derivatives, then it would be a different, then I'd have to use some more general notion of momentum. Yeah.
When you say at solution to what?
Of the equations of motion.
Basically, when you hold the endpoint fixed?
Well, if we take the action and demand that it not change to first order when we hold the endpoints fixed and otherwise vary the world line arbitrarily, that gives us the equations of motion, as we saw in the time-like case already long ago. That's what I mean by the equations of motion. But once you have the equations of motion, it doesn't matter where they came from, right? They don't imply anything about what the world line and what variations you're doing. They're just the equations of motion. So when I say add a solution, what I mean is that the unvaried world line, so in other words, we're talking about a variation that takes gamma to gamma plus delta gamma. That funny equal sign and the words add a solution means that this unvaried gamma, that's supposed to be a solution of the equations of motion. If it's not, we could write a more general thing, but we would have the variational derivative. We'd have this thing. We'd have basically the acceleration coming in. We'd have some integral. So if you don't impose that condition, then you have something like you'd still be able to write the variation of the action, but you'd have some integral term. Basically, here you'd see the equations of motion plus p dx. So there'd be two terms. So what's here is really the equations of motion. That's how you get the equation of motion, right? Basically, you just vary the Lagrangian, you do an integration by parts, that produces a boundary term, and what's left over is the equations of motion. So this is a completely general. So this, I don't have to put this funny symbol. All this funny symbol is doing here is it's telling us that we can set this to 0 because we required the unvaried trajectory, world line to be a solution. Okay? Is it good? Yeah.
Just a question about the reparameterization.
Oh, okay.
Action.
This was meant to be just a by the way remark.
Yeah, but does that have something to do with diffeomorphism?
Well, it's diffeomorphism invariance on the world line. So it's like a one-dimensional diffeomorphism invariance, yeah. So in the case, it could have been called diffeomorphism invariance, but somehow tradition or something has decreed that in the case when you're dealing with a one-dimensional manifold, you often just call it reparameterization invariance. But that's what it is. It's diffeomorphism invariance on the manifold, which is this world line, which you've introduced by introducing redundant variables. If you remember when we discussed about diffeomorphism, general covariance and so on near the beginning of the course, I think I said from a certain point of view, whenever you have a gauge invariance, it means that you have a redundant description. You've introduced extra variables in the extra mathematical objects that in some sense didn't need to be there. And you're just saying that you can change them without really changing anything. So in the case of space-time diffeomorphism invariance, we really don't know how to write the theory without these extra redundant variables, but here you can. So that's all I'm pointing out. So I think normally most people's instinct would be, if you can, then you should, because then it ought to make things easier. But sometimes people do. I mean, anyway, yeah, it's one-dimensional diffeomorphism.
You have a hard time quantizing that because of the 1 over n?
Yeah, although people have certainly done this as an exercise. If you put this in Hamiltonian form and not in Lagrangian form, then it goes up into the numerator. And so then it looks like a Lagrange multiplier. That's what you're probably used to if you're familiar with the canonical formulations of GR. So where were we? Oh yes. So just defining this notation. So this is the definition of the momentum, and I just mentioned the definition. Well, you can see ahead of time that this definition is consistent because you just count the number of derivatives, like I said. But we'll also, when we take the variation explicitly, then we'll see that it does have this form. So just accept that it has this form. In fact, later we'll see, when we take the variation, we'll see that what PA is. It's just GA A dxa d lambda. Or just for short, P is equal to dx d lambda. Which we already saw in the massive case, because we saw in the massive case, of course, you know that P is just m times dx d tau. And using that relation between d tau and d lambda, you can see that it's that m dx d tau is dx d lambda. Okay. So in the massive case, it corresponds to m dx d tau, which we know. But it's important that I'm not assuming any of this. I mean, we'll see that this is true and is what you would expect, but I'm not assuming this. All I'm using is this definition of the momentum in terms of variations of the action. Now I claim we need an intermediate result. I claim that, so this was the definition. It told us to fix the initial world line and allow the final, the initial endpoint, and allow the final endpoint to vary. What will we get now if we allow them both to vary? So I claim that if we allow them both to vary, it follows from what we just wrote above that again we get, I'll just write it as p dot dx, but now it's the difference, it's that same term, but another term comes from the variation of the initial endpoint, which is just the same thing with the minus sign. So in other words, it's p dot dx final minus p dot dx initial. Now, and why is that? Well, that follows sort of from, again, without any work, just from a simple calculation. Let me draw the world line again, a world line. And I'll just label them 0, 1, 2, because I don't know what to call the intermediate one. So instead of I and F, I'll call them 0 and 2, and then this. Now, if we vary, we know what we get if we vary just the final endpoint, but we also know what we get for the variation of this bit of the action if we vary just one. And putting that together, it'll allow us to tell you to see what we get for variation of this second half of the action when we vary both at 1 and 2. So in other words, what I'm saying, if there's room, is that, let's see if I can fit the count. So we're saying, if we consider the variation of the whole thing, we know that And again, we'll assume that before we take the variation, this curve gamma is a solution of the equations of motion. So I'll write this symbol. We know that that's equal to p dot dx 2, let's say, right? But we also know that that's equal to, we know because of the additivity of the action, here's a place that the first derivative nature is sneaking in, notice. We know that the variation of, we know that the action between 0 and 2 is the same as the action between 0 and 1 and the action between 1 and 2, right? Because it's just some integral that we're doing over the world line. And because there's no second derivative, if there were a second derivative, you'd have to worry, because if they met like this, you could get a delta function contribution. The action wouldn't necessarily be additive in general. But here the action is additive in general, as long as we assume that the world line is continuous. And so therefore, well, this is also true at a solution, right? But this is also equal to ds01 plus, because of the additivity, ds12, which is equal to, again, since we assumed a solution, so we're varying, oh, I should say, we vary now 1 and 2. So I'm still holding everything fixed at 0. Okay, so in this little calculation, I'm varying only at 1 and 2. So ds01, it's the same story again. We varied the final endpoint of that bit. So it's p dot dx1. And then we have the variation of ds12. So this, if we set this, this is writing the variation of the full action in two different ways. On one hand, it's p dot dx at 2. On the other hand, it's p dot dx at 1 plus the variation of ds12. So if we put those two together, then it means setting them equal, it implies, well, I wrote the equation down here. It implies this, that the variation, except I didn't have the 1 and 2, it implies that the variation of s between 1 and 2 is equal to p dot dx at 2 minus p dot dx at 1, right? And that's what I wrote here, except I called 1 and 2 I and f. Okay, so it's actually trivial somehow. It's just using the additivity of the action. So we need that. So all we've really used so far is we have some action. Its variation takes this form when you vary the final endpoint. We use that to define the momentum. And from that we derive this slightly more general version of this equation, which tells you that the variation, when you allow arbitrary variations of both endpoints, is just p times the variation of the final, of the position, final minus the same thing initially. So it's the difference of p dot delta x. Okay? So from that we can derive conservation. This tends to disappear, doesn't it? Okay. So now we can use this to show how conservation, in the presence of a variational principle, follows from symmetry. So what's known, of course, that's known. It doesn't stay put. It's known as Noether's theorem. So it's conservation from symmetry via variations of the action. So there's nothing, it's just words really now at this point. let psi be some killing vector. And drag, here's our world line, gamma. And here's our killing vector, psi. Okay, drag the world line gamma to some new world line through the killing vector. In other words, we will let, so this is called dragging sometimes, or lead dragging. Just drag gamma via C. What that means is that we write x equals gamma of lambda as usual, and we let dx, the variation, delta x, be just, let's call it epsilon times C of x. So whatever the value of that vector field C was, at that point, along the world line, we transport that point to the infinitesimally nearby point defined by the vector field C. Okay? Huh? What is this? Now, I claim this is another one of these obvious things that are supposed to be obvious. So I claim that obviously in this process, the variation of the action is 0. Is it obvious? If you think it's obvious, raise your hand. Only one. This is okay. This is so here's the way to make it obvious. Remember, I mean, it's only because I said that C was a killing vector, of course. Otherwise, I would have just put it in a general derivation. So what does the action depend on? The action depends only on two things, the world line itself and the metric. If I were to drag both, I'll just say it in words now. Tell me if you want me to write something, but this is just listen to them. If I were to drag both of them, I would have dragged both the world line and the metric, and so nothing would have, that would just be an overall diffeomorphism of the whole thing, and the action could not change. What I've done here is I've left the metric alone, and I've deformed the world line. That is, I performed an infinitesimal diffeomorphism on the world line. But it's equivalent, since if I do if I drag both of them, nothing changes. It doesn't matter whether I drag the world line gamma forward or I drag the metric backward by an equal amount. It preserves the same relation between them. Or to put it another way, I could first perform this variation, getting the new world line, which maybe I should. Getting this new world line. Okay. Then I could do a second step in which I drag the whole thing, both metric and world line, backward through C. Now what will happen? I'll be back to the original world line, but the metric will have gone this way. So I will have applied, but what does it mean to drag the metric this way? That means that in the second step, it means the variation of the metric, because I'm going backwards, is equal to, or is it forward now? I think it's plus, actually, is leak C of GAB. And when you drag an object forward, you have to put a minus sign. It's the usual story, the derivative. If you change something by its derivative, you're pulling it backward. So you have to move it forward. Anyway, the important thing is that this is equivalent to leaving the world line. So maybe I should write that in words. So it's obvious because varying, what is this? Gamma without varying the metric is equivalent to varying the metric without gamma. When there's a minus sign in there, that is the the diffeomorphism that varies gamma without varying the metric is equivalent to the inverse diffeomorphism applied to the metric and not to gamma. And the reason is if you apply a diffeomorphism by equivalent to, I mean it produces something that general covariance tells us is the same physical situation. Since varying both does nothing. Okay. So this is conceptually tricky, but it's there. It's in the background of a lot of things. I mean, it's quite widespread relationship. So once you accept that, this variation that I've done can be done equivalently by dragging the metric and not touching the world line. But we said that this was a killing vector. So if it's a killing vector, that's where we've used that it's a killing vector. Then this variation of the metric does nothing. Okay. So now how many people think it's obvious? Great. You're not just saying that to be nice. No, that's good. So if it's obvious to you now, then yeah, that's good. So what do we learn? So we learn that in that kind of variation, through a killing vector, we just saw that the variation of the action will be 0, and that's equal to PA dxa, as we just saw, between final and initial, which is equal to PA. But dxa, remember, was just C, although you're not worried about the epsilon, it's just CA of x between initial and final. So therefore, PA initial equals P dot C final. This is conservation. So P dot A is conserved. If I didn't put that in a box, PA So you see, this is completely general. You can use this over and over again in different contexts. And it shows you exactly how a symmetry, given an action principle, how a symmetry gives rise to the conservation law and what the conserved quantity is. As I said, it's a special case of what's called Noether's theorem. A side remark is, which I won't dwell on now, for m equals 0, but we'll see, just to save time, I won't say anything more about it right now. But when we come to derive the conservation direct from the equations of motion, or I should say indirect, really, we'll have to get the equations of motion. But then once you have, if the conservation law is valid, of course, it must also follow from the equations of motion. But in that case, we'll see this again, what I'm about to say now. We don't really need a full killing vector. We only need what's called a conformal killing vector. That is, it only has to preserve the, basically what it's saying is it only needs to preserve the causal structure of the space-time and not necessarily the volume information. I'll define it again in a sec when we come to it. Or if I don't, remind me. So the only thing we have the conservation law, but before we can apply it to, say, the orbits in the Schwarzschild metric, we need to know more concretely what is this P in the particular case at hand. And basically, I could have written any action down as long as it depended only on first derivatives, and I would have got this result. But now we want to know what is this momentum in the case where the action is actually this expression. Okay. So to do that, we need to take the variation explicitly I probably should have, just instead of in words, I should have used a symbol to remind that this is varying about a solution. So anyway, we need to derive this equation that defines, we need to derive what is P in this equation, which basically means we have to go and rederive the equations of motion. We need to actually go through, vary the action, and show what pops out as the boundary term. So what we're going to do is basically, so we want to know what is PA. And to do that, what we're going to do is we're going to rederive the geodesic equation, sort of what you might call from a higher standpoint. In other words, meaning being able to take advantage of the affine connection. Now, the following calculation might look a little bit complicated. So let me say if you remember when we described the equation of motion, when we derived the equation of motion in a coordinate chart a while ago, we had this world line, and we had two kinds of variations, as you might say. Dx, that is the change in the location, change in the point, the space-time point along the world line, and we also had the variation of the world line, which I called in the one case dx as usual, and in the other one delta x. And we used the fact that in a particular, if we worked with scalar, with the components which are scalars, that the two variations commute. What we're going to use now in the following derivation is that even if we apply them to tensors, vectors basically, then they still commute as long as we compare the vectors by parallel transport. So that's the basic fact that's sort of hidden somewhat in the slightly messy calculation that we're going to do now. So let me take that picture that I just erased and blow up a little portion of it. So this is the unvaried world line. This one is the unvaried world line in my picture. And now I'll introduce two vector fields along it. This one is this is the dxa, if I give it a delta, sorry, that varies the world line to a new world line, which I can call gamma plus delta gamma. And then this one is dx a. So if you remember, if you want to be more precise, you can say, if you want to, one way of implementing this idea is to think of x as being a function of two parameters, lambda, the one that's always there, and a new parameter, mu, such that mu equals 0 corresponds to this unvaried world line. And this one mu is equal to delta mu, let's say. Okay. As we did before, as we discussed before. And then if I do that, then I can think of dx. That's really just dx d lambda times some d lambda. It takes you. So varying lambda is taking you along the world line, and varying mu is taking from one world line to the neighboring world line. And then this delta of x, that I can define as partial x, in the sense that x is a function of lambda and mu. It's partial x, partial mu, times what I'll call delta mu, the infinitesimal thing. In other words, I'm using the symbol d is representing basically d lambda times partial lambda, and the symbol delta is representing delta mu times partial mu. Okay? And if you're very careful, you might notice I'm assuming here that the world, that was I vary lambda and mu, I sweep out a nice, smooth, embedded submanifold. In other words, a nice two-surface. So you don't really need this assumption, but I think the way I'm going to write the equations now does use it. Okay. This is the generic case somehow. Anyway, so other cases are just limits of this. So now, the important thing to notice is, think back to when we defined Lie derivative. So if I go, if I vary lambda, I go here, then I vary mu, I go here. But if I started at the same place and vary mu, go to the neighboring world line, then vary lambda, I've assumed that because of this equation here, I'll get to the same place. No matter which order I vary lambda or mu in, I'll come to the same point. That means that these vector fields mesh, as it's sometimes called. Remember, we saw that the condition for that was that the Lie derivatives of the one with respect to the other is 0, if you remember that. And we wrote a general equation, general notation, given two vector fields, u and v. We defined that to be the Lie derivative of v with respect to u, which is minus the Lie derivative of u with respect to v. That's our definition, right? Remember, the condition for this to be 0, to vanish, was that the two meshed. In this case, they do mesh, so it means that these two vector fields, dx d lambda and dx d mu, these are vector fields, right? And that it means that they vanish. So what it means is, if I multiply through by these d lambdas, I would have called this vector field delta dx, and I would have called this delta of x. So I could write it like, I could also say this, delta x and dx commute. That's what I was talking about before. Oh, yeah, in this case I will write that u commutes with v, if that's true. So now we have to do, so we're going to use that at one crucial point in the calculation to switch the order of, we also use, maybe I should remind also what the explicit formula for the Lie derivative was of one vector field with respect to the other. It has, as always, this gradient term, and then it was, since it's symmetric and since it's skew, it just has minus the opposite expression. Right. In case this vanishes, it means that if it means that this commutator, whatever you call it, that equals 0 if and only if u dot grad v equals v dot grad u. That's what we're going to use in the calculation. So that's just to set things up. Now let's write S. Let's just write down what S is and carry out the variation, which we can think of as a function of mu, because mu determines which world line we're talking about. So it was 1/2 the integral of d lambda g dx d lambda dx d lambda. And then there was minus 1/2 minus m squared over 2 integral of d lambda. Now we want to vary this, of course, between two endpoints. So here I've called them 1 and 2. So I'll call them, before I called them I and F, initial and final. So we want to vary it between, we want to carry it out between the two endpoints, and then we want to vary the action under that condition. Of course, when I vary, the way I've set things up, when I vary the world line, that is, when I vary mu, lambda doesn't change. So this thing doesn't vary. So the variation of this is 0. And it'll be 0 when we take the variation. So I can drop that. And so I only need to do the first part. So the variation of the action now is equal to 1/2 integral. I'm not varying lambda in the variation, as I just said. So I'm using that the variation of lambda g lambda, that delta is 0, because it's equal. Because remember what it is. It's just delta mu times partial mu lambda minus if I apply it to lambda, it's partial lambda partial mu, which is 0, since they're independent coordinates. So what I need to do then is just vary this expression here. If I write it out more fully, it'll be GAB dxa d lambda dxb d lambda. And now and this 0 is gone. This term is gone. So obviously I'll get two types of terms. This is symmetric, so I'll get a contribution from varying the metric, and I'll get a contribution from varying the velocity vector here. And there'll be two of those. So the first contribution will be before doing that, I want to do something else. This number is just a scalar. So I'm just asking to vary it. I'm asking for the difference in the value of this quantity, this scalar, between some point and the varied point, the corresponding point on the varied world line. So that I can write as delta of x, the variation of the world line, c times the gradient of this expression, this scalar, right? I didn't actually have to put here the covariant derivative. I could have put the ordinary derivative. But I wanted to put, because this is just a scalar, just a number, but I want to put the covariant derivative because now I can pass it through the metric. That's the big convenience here. So So now I get, as I said, 3 terms. All I have to do is form the covariant derivative of each of these things, but the metric has 0 covariant derivative, of course. So that won't be there, and I'll just get each 2 terms which are equal to each other by symmetry. So the 1/2 will go away. So I'll have d lambda, variation of xc, GAB, we'll put the GAB over here, dxb d lambda, and then I'll have the thing that acts on this, which is the gradient with respect to c of dxa d lambda. Right? since, of course, since the gradient, the covariant derivative of g vanishes. Now I'm going to use this fact that the vector fields delta x and dx mesh with each other. So I can rewrite this. This is, see, this has the form of some vector field added into the gradient applied to another vector field. Since they mesh and the variations of lambda are 0. Oh, I should also point out, this came up once before, but let me point it out again. We only really know what these vector fields are on this 2 surface, consisting of the world line and all its variations. This looks like it would depend to form this covariant derivative, but I need to know it off the surface. But I'm dotting that in with something that lies in the surface. And in fact, that means that this combination only needs to know what's on the surface. It only appears to depend on something off the surface. So, which we saw before, but I can't remember where we saw that same thing. Anyway, let me rush a little bit. So, okay. We saw it. I can't remember now, but that fact came up before. So I can replace it. This is of the form, this has the general form of u that we saw over there, u dot del v, and I replace it with v dot del u using this fact here, that the 2 vector fields mesh. So if I make that replacement, then it equals d lambda. Now I have to put here dxc d lambda grad c, and here I put delta x a, right? So that's the key step. And then I still have gab dxb d lambda. And I think I might have too many. No, that's it. Okay. Now everything is sort of clear sailing. It's only one more step or two. It's the usual story. I've now got the variation of x under a derivative. I don't want that if I'm deriving the equations of motion, so I have to do an integration by parts, which means I have to rewrite this I have to take, I have to throw the derivative in the other direction. So what do I want to do now? Let me cancel these. So I can just write this. I don't need these 2 lambdas here. So I have just dxc, gradient of c. This directional derivative along the world line gamma is what this is. I just want to integrate it by parts. So I'll now apply it to dx alpha, dxa, gab, dxb, d lambda. In other words, I'll take this stuff here under the derivative, and then to compensate, I have to do d lambda the delta xa, and then I have dxc d lambda gradient of c. I have to apply it to what's over here, which is GAB. But the GAB, as always, the GAB can come out. So I have gradient What have I done here? Yeah, dxc, dxb. D lambda, and then I have the GAB, right? I think I did that. Okay. Now, what are these two terms? This is just this is now a scalar here, and this is just a directional derivative along. This is just d by d lambda of that object. So if I restar the lambdas, so this is equal to d. The first term is equal to the integral of d of this scalar between 1 and 2. And the second term is equal to d lambda variation x delta x a dxc d lambda grad c acting on this combination. So now remind you the notation we used before. This is just a vector field with a slightly different, well, I can leave it like this. GAB. But now this thing, this is just the direction. Remember, this we call d by d lambda, if you remember. It's the covariant directional derivative. So this whole thing here is just d by d lambda of dxb d lambda, which is the second. It's basically what you might call a x double dot. It's the second derivative taken in the covariant sense. It's what we call the acceleration. This thing, of course, is just equal to this object between 1 and 2. What was this object? It was delta x. So now I write it out explicitly. It was GAB dxb d lambda times delta xa taken between 1 and 2 minus the integral d lambda delta xa, and now what I can call the acceleration, have called the acceleration a, where the acceleration is defined by this equation. It's d by d lambda. Here I used this GAB to lower the index on the acceleration. It's d by d lambda dxa d lambda. So this was the acceleration. Colloquially, you might just call it x double dot a, which means the double dot is with respect to lambda here. Okay, so that's the result. So this is completely general. I haven't assumed anything. So I haven't yet assumed that I had a solution of the equations of motion. So what I've done is actually derived the equations of motion, right? On the one hand, so this is the usual story working with variational principles. On one hand, we just say, well, this delta x was supposed to be arbitrary except at the endpoints. I mean, the delta x was supposed to be arbitrary. If, however, we say that it vanishes at the endpoints, then we require the action to vanish, the variation of the action to vanish. So if it vanishes at the endpoint, this term will be 0. And this term, therefore, must vanish. And it must vanish for arbitrary delta x everywhere except at the endpoints. Therefore, it means that the equation of motion is just that a equals 0, as we saw before. Okay, that's the same thing that we know, what we've seen before, but now we've derived it also in the case of a null world line. And then once we are at a solution of the equations of motion, once our unvaried world line does solve the equations of motion, we're just left with this endpoint contribution. Right. But this was what we defined this to be p, the momentum, the thing that multiplies the variation in x when you vary the endpoints. And so what we've learned is not a big surprise, is that PA is equal to GAB dXA d lambda. It's not a big surprise in the massive case because we saw that just goes over when the mass is greater than 0. It just goes over to m dx d tau, which is a very familiar expression for the momentum. In the massless case, it's a little more subtle. It depends on lambda. But it's still something tangent to the, if we raise the index, make it a vector, then it's a tangent vector to the world line, but the exact way it's normalized depends on this lambda. So the equations of motion are the same. So if we now view the massive and massless cases together, we can say the equations of motion are the same. I can write them like this. That's the statement that A equals 0. We have exactly the same equations of motion. And what it says, this is the tangent vector. You might call it the velocity vector. What it says is that the velocity, remember what this means? That means that the velocity vector, what this means is that we can pair when we form the derivative by parallel transport. So it says the velocity vector, which is just dx d lambda, is parallel transported along the world line. That's what the equations of motion tell you. And then the other big thing that we learn is this, that the momentum, the thing which is conserved when there is a killing vector, is, or its component is conserved when there's a killing vector, that thing is just the velocity vector in these, when we use lambda as a parameter. Okay. So incidentally, this is a second proof proves that our old Christoffel symbol and our new Christoffel symbol are the same. Once you know that the new one is also symmetric, which will be in a homework. So that's essentially all. I wanted to say a little bit about what is the meaning of this d lambda, but let me just raise it as a question. Maybe I'll start next time by showing one way of thinking about it, what it is geometrically. But I don't think, as I said before, I don't think it completely clears up what its physical significance is. But anyway, it's there and with this variational principle. And with that, and it does, by the way, I should mention, and in the case of a null vector, this is, of course, the condition of a null geodesic. This condition is that it be a geodesic. And if the vector is null, it's a null geodesic. And this lambda, remember, is called an affine parameter. So this equation tells us that whatever lambda is, it's an affine parameter along the geodesic. I think when it comes to, if you think in terms of a quantum particle, then or a wave packet in geometrical optics, you can relate this, well, in fact, I know you can relate this lambda to the wavelength of the particle. So that's perhaps one way of thinking about, of understanding why it's there. But in any case, that's what comes out of the equation. And then we'll be able to use this conservation law then for both photons in orbit around the sun and also planets. Any last questions? Okay, so see you Thursday.